My name is Sandra Scott-Hayward. I'm a lecturer at Queen's University, and the research I do is in software-defined network security. So I thought I'd talk a little bit today about monitoring in SDNs and for the purposes we look at it from a security perspective. So one of those purposes being intrusion detection and prevention systems. So some of you may have seen our beautiful Lanyon building up at the main Queen's campus. That's been around for a fair while. CSIT is our Centre for Secure Information Technologies, which is the research institute I'm based in, and that's based out in the Titanic Quarter. So that's been there for about 16 years, the building, and this year we celebrated the 10th anniversary of CSIT. So the research I'm looking at is SDN security. So first of all, I guess, raise your hand if you've heard of SDN and NFV and/or NFV. A good number of people, okay. Anybody who hasn't, basically software-defined networking, if you take it down to the bare bones, refers to separating the control and data plane in the network elements. So we introduce a communication path between the controller and the data plane. And that's allowing us to introduce programmability into the network and giving a bit more control over the network from a centralized or a logically centralized perspective. So it's really introduced for flexibility in terms of operating and running the network and upgrading the network as appropriate. And network functions virtualization then is virtualizing traditionally hardware appliances of networks such as load balancers, again IDS and firewalls are things that we've talked about a little bit today already. The two sides to the SDN security story then, one is looking at the vulnerabilities within that new architecture. So we're separating out control data, and we also introduced the idea of having third-party applications operating on the network. So there are a fair few vulnerabilities in there. I'm not talking about any of those today. We have done some work on those. Several of them, obviously SDN itself has been around based on the OpenFlow protocol, which is the communication protocol between that control and data plane. It's been around already almost for 10 or 12 years. So a lot of those early vulnerabilities within this new or no longer new architecture have been ironed out. There are still many to resolve, but they're looking at more some of the deployment issues today. The piece I do want to look at today is then talking about the monitoring, the idea that we can actually exploit this idea of logically centralized control and programmability to perhaps enhance, make more efficient our network, both to resistance to attacks and resilience and proactively detecting attacks in the network. So that's what I'm going to talk about. I split it out into the 5 Ws simply for well, I thought it was a reasonably catchy title. That's for you to judge. But I'll go through each of those questions just now. So the why we can kind of take out of the frame fairly quickly. We all know that our networks are under attack. We had a great talk earlier on from Carrero on the multi-vector DDoS attack. So it's not a question really of answering why we need to do it. We know that we have to introduce this. The motivation for doing it, particularly from some of our the business aspect of it, is that it is a cost. This is just some figures here from the government department, talking about the cost to UK businesses and charities. You can split that out into time cost and also the monetary cost to businesses that are being attacked day in, day out. So we can set out, okay, we definitely want to be monitoring what's going on in our network. We definitely want to be doing early detection if possible and proactively protecting within the network if we can do that. So who are we trying to monitor within the network? Now, when Asim was talking earlier about the Carrera, the DDoS example that he gave, he showed the spoofed IP addresses. Now, many of you will have heard of the Mirai botnet. It's a famous attack about 3 years ago now. And the exploit there was based on the volume of devices, Internet of Things devices that we have across our networks, and the vulnerability of those devices not being designed from a security perspective, being put out into networks, deployed, everybody having devices that are connected to the Internet. And in this case, what the attackers do, you can see probably not terribly clearly on here, but you've got the devices themselves are scanning out and looking for, the first part of this is open or default password settings, that they can simply get on to neighboring devices and then advise their command and control to download the exploit, whatever it's going to be. In the Mirai case, it was to command a DDoS to take place, a distributed denial of service attack to be undertaken at some point in time. So the point of identifying this is saying, okay, well, we're looking at where we're going to detect these attacks. So maybe we need to think about who we're attacking, not in the centers of our network, but further out towards the edges of the network at these devices, these edge devices. Can we do some understanding, or can we make some understanding about what's going on there? Perhaps identifying the scanning behavior, which we can later then build into our protection mechanism. So, as I said, these devices are pervasive. We're doing smart everything, smart environments, smart sensing, smart homes. We've got this huge volume and growing. So it's becoming more and more of a challenge. And SDN itself as an architecture can help us to get a little bit closer to those devices in terms of the monitoring and in terms of the protection itself. So this illustration is a simple overview of what we get. So I mentioned before, these network elements are our SDN switches, for example. We have a protocol to communicate. Open Network Operating System is an example of a distributed controller environment for high availability. And in a simple example of protection, we can do some monitoring with our sampled S-flow, for example, detect our denial of service, for example, in that environment. We can set up applications, security applications, connected into the controller. They can either be co-located with the controller system or third-party applications in the visionary idea of SDN. I think, as I mentioned, from the vulnerabilities perspective, people aren't that comfortable with having third-party network applications running on their network operating system. But the facility would be there if we wanted to go more innovative in that sense. So, an example of how this works, we might sample with our S-flow information, take that information from the switches about what traffic is passing, what flows, what's going on, detect an event using our SDN application, and then we'll use the open flow communication to program the network for the protection. So you've always had the S-flow in place there. Here we're just saying that at a switch level, we can start reprogramming and automating some of this protection mechanism from this kind of an approach. And you can do other things like introduce the blacklist. We were talking earlier about blacklist and blocking of known malicious sites. You can have a set of devices, a set of list of devices that you want to block or IP addresses you want to block. And in this case, you would set up monitoring rules within your devices to actually detect when you identify one of those IP addresses of flow, and then pass that to the controller for processing to check whether it's going to require blocking or not, whether it's malicious, potentially considered malicious. So you can do all of that part of it through this open flow protocol. But all of you, I guess, are well versed in network operations, and you can detect the obvious flaw in this process. So that's the passing of all of this information back up to the controller. Not only from the volume of information that's communicated, it's being sent on that control path, which can introduce your own denial of service if you're in an attack situation, you're sending a lot of information up, but also from the processing. And these tiny little graphs that don't worry about seeing the figures on them, but we've got across the top here are the three controllers, a measure of their CPU and memory usage. So when we did some basic measurements within the lab just on a distributed controller and a series of switches, what we identified was immediately that when we set off a 3-second, a short DDoS attack, our controller's overwhelmed with trying to process all of this traffic, all these flows that it needs to actually do something with. The switches, on the other hand, are well scoped to cope with those, and that was just a virtual switch implementation of Open vSwitch in that case. So what's happening is you're getting all of these flows being sent up to the controller for decision making, essentially, and it peaks at some point, and then the network will recover once the attack has stopped, for example. And again, here what you see is not the absolute values, because I don't think any of you would deploy this on a network with those kind of protection times, but the network recovery time, as you increase that attack, it just increases to a point where the network no longer recovers. So that was our first sort of exploration of how we can do this, kind of exploiting a bit in terms of being able to do a very quick protection that you can automate in the network, but seeing that it's not really feasible to have the controller and the open flow communication in the mix for that. So that's looking at sort of like the who, the what, and the what that you're monitoring. So when we actually place the monitoring, then the idea with OpenFlow is that you have not only matches of the flows and an action that you take on it, so you might drop the flow or allow it or pass it to the controller or simply forward it on through your network, but you also have statistics attached to that, and that would replace then the example of the S-flow statistics, the sampling flow information that you get out. But the polling interval obviously has a large impact on the amount of information that we're passing through here. So it's a trade-off then. Okay, the more flows you have in your network, how frequently do you poll that information? So you're trying to engineer it that you're monitoring. You're not missing an attack, but you're also coping and speccing out the network to what it can manage. And this is again just an illustration of what we were showing on the previous slide, where when we did this is introducing a little bit of machine learning into an application for a SYN flood detection. When we did that using Ryu, which is another SDN controller, you see they get a huge variance in the detection accuracy based on that interval of polling that we set. Whereas Argus, which is a system for mirroring all of the flow information, can give us a pretty satisfactory accuracy level consistently on that. So we kind of identify from there, and there's been a lot of work done around that field, like we're not going to be necessarily using the open flow polling statistics for our key attack detection or intrusion detection within the network, not in isolation anyway. So what we did to try and address it was to introduce a system, and this is a platform that we developed with Lancaster University called TENNISON, where we do multi-level monitoring. So I'm not going to go into all of the details, I don't have a huge amount of time today, but basically we build into this system a series of different security applications and policies that we're checking on. We also introduce some virtual instances of IDS, so known IDSs of Burrow and Snort, for example. And then we use a combination of different monitoring techniques. So we'll scale it up from a high volume but low detail or sampled polling at the bottom level, and then right up to a higher granularity. So for certain flows, when we suspect something's going on, we can switch on the DPI, the deep packet inspection type capability. And the other thing we can do here is also look at, so what I showed in the original slide there of that impact on the controller usage when you're processing a lot of flows. Obviously the IDS or IDPS isn't the only operation that's going on within the network. You've got a lot of other flow management processes in place. So if you have a controller that's managing a series of switches and it's experiencing a high volume of traffic, then we can offload some of those switches to another controller. So we can look at the resource monitoring in the network. So try and balance things out. So you're constantly trying to adjust the monitoring as appropriate to the attack scenario or to the resource usage within the network. So that's the when, so varying it in accordance with what's going on, the network state at the time. Then we think about, okay, if we think back about the Mirai idea of the edge, is it better to detect early on in the network? Can we use that, or are we better to place this functionality at the core? Now, the beauty of SDN, obviously, is that if this is in switches and controllers, it can be multiple points in the network. We're not trying to fix a point within our network where we placed this hardware appliance where the traffic has to pass through it. We can actually redirect the traffic to pass through wherever we have our control system or our IDS virtual instances in place. So this is an illustration of a pub-sub type integration into an SDN. So the idea would be here, and we did some again, this is a sort of just a proof of concept, but where we have a botnet type detection, that's the example being the Mirai scanning phase that we look for. There are some very identifiable footprints within that, or signatures within that we could detect on. We detect that there's some activity in one subnet. We can use the controllers linked into a pub subsystem, in this case Apache Pulsar, and we can then identify if we want to push out, we've got some subscribers looking also want to find information about the DDoS attack, for example, and we can push out the protection mechanism proactively. So you don't necessarily need to have the detection mechanism operating in these. If it's identified in one part of the network, we can tell the rest other neighboring parts of the network. There's a similarity there related to the idea of the ISP or the flow spec implementation, but it's a little bit more generalized here. The other direction, and anybody who does know a lot about SDN is probably waiting for me to mention P4, which is programmable data planes. So the idea of programmable switches. And this is the obvious transition. We've been looking at it for 3 or 4 years now. So OpenFlow being a methodology or a means to program the switches, but it's programming a fixed function switch. So to do similar operations and handle similar protocols that we already know that are deployed today in our network, so we understand how the packets will be processed in those devices. With P4, the idea is that you can actually program the switch to handle whatever. You can write the protocol, new protocol. You can map the memories to do whatever different longest prefix matching, whatever you want in terms of the mapping of it. It's got a couple of, quite a few benefits from this perspective. Here, the idea is that we can actually do our monitoring and our protection within the device for some functions within the device itself. So we no longer have to report back up to the controller and integrate that for certain signatures of attacks that we're aware of. We can build those into the thing. So we've got examples of being able to do that for DDoS. Got a student here who's looking at doing DNS exfiltration detection, placing some of that into the data plane as well. So this is just an illustration of the P4 switch. So you have parsing that you can actually write how you want to parse the packet. You can write the match action, and you can write how you actually manage the whole processing of the packets through the device itself. And as I say, use the registers within the device to do some tracking and program any changes. Essentially, it's an advanced version of a stateful switch. So there have been some attempts between OpenFlow and P4 to add statefulness to OpenFlow, and this is the ultimate to date in terms of that. And this is just an example to show you how in-band network telemetry is being deployed with P4, is envisioned with P4, and ONOS, that operating system that I mentioned. It's an open source tool. So you'll have in-band telemetry sources where you'll place in the flow rules. You say, okay, here I want to start adding int headers. Here I want to, at some point in the network, you want to capture the telemetry metadata, and then you'll have some point where you actually sync that information, you can send it out. Now you can sync or export at least from all of the devices, but obviously there are different ways to do it from an efficiency perspective. So that's one example of that. Finally, the what. So we know we can get a certain amount of information. We know we can get increasing volumes of information. And if anybody followed the OpenFlow spec, they would have seen an increasing number of header fields that you could match on, expanding for the different protocols we wanted to look at. But what is actually interesting or useful within the network information? So this is a little experiment we did with you designing a kind of, again, sort of motivated by the Mirai botnet defender. So looking at, this is using Argus, so here we're mirroring, so we're just using SDN in this example for programming the block or the protection mechanism. But we export the data, and you can see we've got a whole series of processes here that we have to go through when we're applying machine learning or data processing here to the attack traffic to identify if it actually is a botnet or not. And that's extremely time consuming. So some of the types of information we can get out are listed here, and this is an endless range almost. I mean, there's something like 43 very, very useful, considered to be very useful for a range of different attack types from the attack source data that we've got. But if you look at an importance measure, which we try and do for the random forest, we use that to identify which of these features are actually giving us or contributing most highly to this algorithm's detection of it being an attack or not. And we see that there are a few that feature very, very highly. So one of the things we need to think about is, well, is all of this information that we can gather off the network, how useful is it? Should we be a bit more sensible about what information we use and how we capture that to improve the efficiencies even further? So that's the 5 W's. Just to recap in terms of the recommendations, where we're at with this, what we're recommending today. The distribution of monitoring is a natural one. It really is a point at this stage where we're saying, okay, we can do a lot of this monitoring in the data plane. Now, obviously, that requires that we move to these types of switches, but there is certainly a motivation to go that direction. I think we're seeing a lot of movement in that, and particularly some of the larger telcos are driving that kind of development. Splitting and coordinating the monitoring, we have a capability there with the programmability that we have, the visibility across multiple domains. We can do the monitoring at the appropriate points in the network and be effective about that. I've just mentioned the volume, the idea of limiting the volume of data that we're processing to sensible volumes. And also employing, like we did in TENNISON, the multi-level monitoring, so scaling it up or scaling it back depending on the state of the network, what's appropriate. And finally, I mentioned this in one of the last slides there because you can't do a presentation today, although we didn't have any mention, I don't think, earlier of machine learning. Normally it's pervasive and on one of the buzzword bingo lists, I think. But the machine learning algorithm I pointed to earlier, the random forest, for example, these rely very, very heavily on feature engineering, and so sort of human interpretation and looking at what's actually going to give the best indicator of the attack, what's the contribution. Work that's being done today, we're looking at using neural networks and convolutional neural networks where there's no reliance then on feature engineering. The network itself determines internally what are the highest contributing factors, creates its own features effectively to determine an attack scenario or attack detection. The converse then of that, of course, is that we don't necessarily know what it's doing and why it's doing it. So although it's beneficial from removing this reliance on feature engineering, now the big questions are always about explainability and interpretability of what it's doing within the device itself. But that's kind of the direction that the contribution of machine learning is building into in terms of our detection mechanisms that we sit then on top of or integrated with SDN. And ultimately then I think the combination, we're seeing not only those being done in software, but the devices themselves being built in with hardware devices being looked at, being able to deploy more and better processing for machine learning purposes. So that was my presentation. I'm happy to take questions, or if you're dying to get to Pints and Packets, we can talk there. Thank you very much.
Thank you, Sandra. Are there any questions on the 5 Ws?
Pints and Packets.
You think it's pints and packets, yeah. I have a feeling that might be a factor here. Thank you very much again.